Okay, so this is a good start on our organometallics and their use. First, organometallics never ever use this reagent because it's not real. The only way that you can make an organometallic is to already have some sort of alkyl halide, vinyl halide, aryl halide, some sort of halogen in your structure. You can use elemental magnesium. You could use elemental lithium. And if you have an organolithium, then you can use copper 1 iodide. And so those are our three types of organometallics. The Grignard, which is more generally called the organomagnesium halide. The Grignard, the organolithium, and the lithium diorganocuprate, or just the cuprate. Not all three of them are useful in the same ways. Actually, I would look at this as two types of organometallics. The type of organometallic that can do acyl addition is organolithiums and organomagnesium halides. These are essentially the same. For example, on the exam, if you write methyl lithium, but my answer key said methyl Grignard, methyl magnesium bromide, those are exactly the same. On paper, they're exactly the same. In practice, they can have differences in solubility or reactivity or whatever, but on paper, these two, interchangeable. These are useful for acyl addition, and the other type, the cuprate, is not useful for acyl addition. Well, I didn't mean only. I meant acyl addition. Remember that everything is little magnets. An acyl addition is a negatively charged carbon running into a positively charged carbon. And the little magnet that is the cuprate doesn't really set free those little carbon negatively charged magnets. So cuprates don't have negatively charged carbons that are free to roam and attack a carbonyl. So the cuprates are just not effective at doing this addition. The other type of reaction that we can do is NAS. Remember NAS as opposed to EAS? Can someone describe the difference? Since it's not on the board, I assume you guys feel confident enough to describe the difference between NAS and EAS. Can you expand on that a little bit more? It has a nucleophile. Most reactions do. Those are two sides of the coin.
Like the charge that moves around is negative.
Moves around what?
In the aromatic ring.
Good. NAS has a negatively charged intermediate in the aromatic ring. During NAS, is the ring attacked by a nucleophile, or does the ring attack as a nucleophile? The ring attacks as a nucleophile. Wouldn't that mean the ring is getting rid of electron density? How would it take on a negative charge if it has just donated electrons? That wouldn't add up, would it? Instead, in order to get a negative charge, the ring has to be attacked and accept electron density. Now it has an excess, and that negative charge moves around. How do you read this? How do you read this? I've read it to you many times. How do you read this name? Do you just read the letters and not think about what they mean? That's a possibility. Do you read it for the words that they stand for? Nucleophilic aromatic substitution, in my opinion, that just goes in one ear and out the other. I don't really know whether that tells me that the ring is the nucleophile or not. It tells me there's a nucleophile involved, but if there's a nucleophile, there's also an electrophile. I want you to read this backwards. Substitute an aromatic ring with a nucleophile. So have the nucleophile attack the ring. Both of our types of organometallics can do this. Then we have SN2. And they can, both types are able to do SN2. Because these are strong bases, they really shouldn't be doing SN2 on anything more than primary alkyl halide. And then the last type was what I had referred to as vinylic substitution. And that is unique to the cuprate. It's not one that I really show you guys all that often. But just for example, it will substitute an aryl halide on an sp2 carbon. So I want you to remember this is not SN2. SN2 requires far too high of energy on this type of carbon. This is a completely different mechanism that leverages copper's d orbitals. Layla, do you have any follow-up questions on organometallics and their use?
I don't think so. Not right now.
Okay, I guess I have a problem for you guys to solve then. Okay, I know that's a lot to write down. These are both acyl addition steps, acyl addition reactions. That's my goal. Can you solve for what is needed over the arrow? Might not be just one step. You might have to say first, second, third. Okay, I want to take you guys through this. When I say acyl addition, what two things are needed? What reagents do we bring together? Well, the aqueous workup definitely has to follow. But what is the organometallic working with, reacting with during acyl addition?
Like a ketone or an aldehyde.
Carbonyl. Yep. We will see in later, we've only said what happens with a Grignard and a ketone or an aldehyde. So in this reaction, where I do an acyl addition, I'm adding across the carbonyl. I already have my carbonyl. So what am I missing? What will show up over the arrow? And then the aqueous workup. The organometallic and the aqueous workup are missing over the arrow. So is that what's supposed to go over the arrow in acyl addition? Over the arrow, we show the organometallic and the aqueous workup. And before the arrow comes the carbonyl. That's how we show acyl addition. What does the arrow mean in an organic synthesis? Does it require one thing to be on the left and something else to be on the top? Not necessarily. So in this bottom reaction, I'm telling you that it's also acyl addition, but in front of the arrow, I don't have a carbonyl. So it doesn't matter which reactant in the first step shows up before the arrow and which reactant in the first step shows up over the arrow, because organic synthesis is about showing what you're starting with and then showing what change you're going to bring to it. So I just wanted to clarify that. You can have the carbonyl or the organometallic in front of the arrow. That doesn't matter. Think about mapping in this first one. I can see that my carbonyl carbon becomes this tertiary alcohol carbon, and I like to count through my nucleophilic attack. My nucleophile is carbon 2, the Grignard. So I want my first step to have a nucleophile coming off of carbon 2. I've decided to go with phenyl or benzyl lithium. You could have gone with benzyl Grignard, but the benzyl carbon is the important part there. The fact that the CH2 off of the ring is attacking. This isn't phenyl lithium or phenyl magnesium. It's benzyl lithium, benzyl magnesium. Maybe it would be a useful time to use condensed bond line structure, because now you can see that there's a CH2 group quite explicitly coming off of the ring. And then an aqueous workup. The second question that I put up here was not meant to be just like a one step. It probably should have been. If you were doing this on a roadmap problem on the exam, it wouldn't be just one step. This would have you go through multiple steps. Because I don't have an organometallic, so of course I'm going to have to first form an organometallic. And that's something that you would likely have to show on the exam. There would be a box for you to put it. Now that I've got my nucleophile, I can introduce my electrophile, but I need to figure out how many carbons my electrophile has. And I wonder if you guys can see it. How many carbons in the carbonyl structure? Two carbons in the carbonyl structure. So here is my my alcohol carbon. The lore of the alcohol carbon is that it used to be a carbonyl carbon. The T, if you will, is that this was the carbonyl carbon. And so this is my nucleophile. 1, 2, 3 attacks. 1, 2, 3 attacks carbon 4. And then 5. Now, remember, when I'm mapping carbons, I don't map every single carbon. I map the most useful ones. And then I keep track of the others. So I've got 1, 2, 3 attacks, 4, 5. And off of 3, I have a methyl group. 1, 2, 3 attacks, 4, and then 5. And I've got a methyl group off of 3. But I'm not done because this is the step that needs both a carbonyl and an aqueous workup. So just over the box, I have to add that aqueous workup, that acid workup. Follow-up questions on organometallics and their usefulness. There is not a large way, there's not a big arsenal of creating carbon-carbon bonds, and that is truly one of the biggest usefulness. That is one of the most common uses of organometallics. It's the fact that they make carbon-carbon bonds. Okay, Mimi, we'll spend a second on mass spec. Whoa. Mass spec works by a magnetic field interacting with charged particles, positively charged particles. And in order to make those particles positively charged, we have to lose electrons. And there's different ways that we can lose electrons. A molecule can lose a lone pair electron. A molecule can lose a pi bonding electron. And a molecule can lose a sigma electron. But it is the sigma electrons that are the least stable to lose. When losing a sigma electron, you create a 1 electron covalent bond. And you guys are most familiar with hearing about how many electrons in a covalent bond? A 2 electron covalent bond. It's so common that we just assume it. Every time we draw a line, we assume that we're drawing 2 electrons. So you can think about this loss of the sigma electron as being the last thread holding 2 pieces of a sweater together. One little disruption and those 2 pieces are going to fly off from each other. And once they disperse, they become 2 separate fragments. Only one of these fragments can hold the radical. The other fragment has then effectively lost both electrons and keeps the positive charge. So if this structure with a 1 electron covalent bond were to become fragments, there are 2 options. One where the methyl takes the radical and the carbon takes the positive charge, the carbonyl carbon takes the positive charge. The other is where the methyl takes the positive charge and the carbonyl carbon takes the radical. And these will produce different signals. The radicals that form in either case do not produce a signal. They're unaffected by the magnetic field. They're pulled into the waste by the instrument. The positively charged fragments, those are deflected by the magnetic field towards a detector where they produce a signal based on their mass. This structure on the left is actually in resonance with the lone pair on oxygen, which stabilizes a fragment. Having resonance is always a stabilizing force. And it means that that fragment on the left, that cation, is much more likely to form than the methyl cation, which has no resonance and basically zero hyperconjugation, zero induction. So while all of these different versions of a molecular ion, all of these would give the exact same signal. Oops. That's our molecular ion. And it would give a signal of 15 plus 13 plus 16, 28, and 16, 38, and 6, 44. They'd all give a signal at 44 mass per charge. But these ions would give different signals, 15 mass per charge, 13 and 16, 29 mass per charge. So based on the signals that we see in a mass spectrum, we can try to figure out what fragments might be, like what parts of the molecule might be in the structure. And I say we can try because there are other structures that weigh 29 mass per charge. An ethyl fragment, just a 2-carbon fragment, weighs 29. That's 15 and 14, as opposed to this, which is 16 and 13. So it's just hard exactly to be able to look at a mass spectrum and say, this is the structure. You get glimpses of ideas, but you'd need to correlate it to an IR and NMR to really get good answers there. Okay. Was that enough, you think? I think that was good. Talking about this split of how much is Unit 1 versus 2 and 3, I want you to think about how much from Unit 1 did you see come back into play again in Units 2 and 3? Because that's a good way to look at how much to expect OCHEM 1 review material to be hidden within like the newer things that we're looking at. So we have talked about forming alcohols. How many of the alcohol, okay, sorry, there's only 2. Of the 2 alcohols up there, can you describe their chirality? Are they chiral, achiral, meso compounds? Are there any chiral or achiral alcohols up there? Did I draw my structure wrong earlier? Or did I not have that? No, I didn't have that. Sorry. I was about to start erasing right as soon as Brenna walked in, which is a very great way to greet someone. Welcome in. You can't look at the board.
Is the alcohol on the top achiral or chiral?
Right, that is the question. Thank you, Justice.
Yeah, I know, but I can't tell. Because like 2 of the substituents look like they have a plane of symmetry. 2 substituents of the ring. But I don't know if that is actually a plane of symmetry.
What do you guys think? They feel Pretty confident. Meaning there is a plane of symmetry. The two sides of the ring are symmetric to each other. And it might not look like there's a plane of symmetry just based on the way I drew it. You can't draw a plane of symmetry down here without feeling like the alcohol is on one side and the benzyl group is on the other, not reflecting into each other. But don't forget, this is a tetrahedral carbon, which means two things are actually coming towards you and away from you in the same plane as each other. And then the ring is coming to the left and to the right. I actually brought my model kits with me for the OCHEM 1 review later, but we can visualize this. If we're to say that we've got maybe the two sides of the ring are the carbon chains here, then actually the alcohol and the benzyl group are directly in front of each other. And if I draw a plane of symmetry that cuts through them, then I don't have four distinct groups. I've got the two sides of the ring that are identical to each other. Achiral, and the one on the bottom, feel confident? What's the highest priority group? What'd you say? Oh, the oxygen. Because we don't look at a group by the group, we look at a group by the atom. We go by the first point of difference. So the oxygen, what's the second highest priority? Right, rather than the primary carbon, it's this carbon that has four other bonds to carbon. So eventually a bond to carbon is going to win out over a bond to a hydrogen. So chiral. I think if you've gone through your practice tests, the past midterms, you would have seen that there's almost always a question that talks about chirality. Even though we don't talk about it during every lecture, we don't talk about it in the context of every reaction, it's still there. And being able to quickly identify chirality and chiral carbons is a useful skill to still have. I also want to say the mechanism skills that we practice in Unit 1 come back, even though you won't be testing on the mechanisms from Unit 1. The synthesis skills that we covered in Unit 1 come back. The nomenclature skills come back from Unit 1. So I would say Unit 1 doesn't look like a heavy part of the exam, because it doesn't look like there's a ton on the OCHEM review, but it's embedded in there. Since we're kind of in this same frame of OCHEM 1 review and mass spectrometry, how do you guys feel on your NMR and your IR skills? Do you want to talk about that then, Mimi? Yeah? Now this I almost always put into the context of new material as well. So taking this acyl addition that we're showing, we're showing with cyclohexanone, and then we're forming this adding this benzyl group. I could frame this as a multiple choice question if you want, but I think I'd rather say, what change would you expect to see from the IR of the starting material to the IR of the product? What change do you expect to see? If you compared starting material to product.
You'd have that big alcohol, dip, if you will.
Is that good? Gain of an OH broad peak above 3,000. I'm only saying above 3,000 because that's what Jordan gave me.
It's like, I don't know, like 30.
But you'll have a correlation table. So you won't have to memorize these for my exam, although I can't say if you're taking an exam after this class, like the MCAT, I can't say you'll be giving it a correlation table. So that's one change that we'd expect to see. The starting material wouldn't have had that in the IR, but the product does. So we'd see a gain of this broad OH. What else? If you're not sure, try pulling up that correlation table. Open a past midterm and look at the correlation table given to you. Because if it's not obvious to you, then you need to know how to utilize that tool to figure it out. Evan, do you see one change that's obvious to you?
Loss of the CO double bond.
And whereabouts would we find that loss?
I'd have to pull up the table.
Any rough estimation? If you had to guess a number.
Isn't it in the 2000s, or is it lower than that in like the 1600 area?
Good, it's lower than that. This, I would say, is like 1700 is a good approximation. Most of the carbonyls come close to having an absorption around 1700. They don't all, like amides are predicted below 1700, anhydrides and acid halides are predicted above 1700. They never come quite to that range, but for a ketone, 1700 is a good approximation. Good. What else?
Aromatic ring peaks.
Tell me more, because so far we've looked at bonds, and an aromatic ring is not a bond.
The first one would be one of the alkenes of the aromatic ring at 1600.
Is it an alkene?
C double bond.
There you go. At what?
1600.
Good. And sorry, gain or loss?
Gain.
Right.
And then sp2ch is the aromatic ring.
Good. Where do you find those?
3150 to 3000.
Cutoff is right at 3,000, so we can say this one's around 3,100. Good. You might also be able to look for the aromatic overtones, which are the result of the carbon-carbon double bonds, but the overtones are not a guarantee. They are sometimes there, they're sometimes not there. So don't bank on the aromatic overtones. So what I do in a question like this, keep in mind, this is just acyl addition. This is unit 3 material, right? How did we form alcohols? We introduced a new way to form alcohols. But it's applying unit 1 review material to it. What I'll typically do in a problem like this is there's so many changes that I'll add 3 changes that you should expect to see, and then I'll add a signal that you shouldn't expect to see. So a gain of signal or a gain of peaks from 3,000 to 2,800. And I'll word the question as, which of the following changes is not expected from the IR of the starting material to the product? So maybe you don't know this, but I do want to tell you this. In multiple choice problems, you should be able to rule out all of the other answers if you feel like you're able to select a correct answer. if an answer comes obviously to you, then it should be easy enough to rule out the others, to go through and prove that they're not the answer you want. All right, what about NMR? What change would you expect to see in this reaction for NMR? Proton, NMR, H1. Change. So what change would you expect to see from the starting materials NMR to the products NMR? There should be no signal that has 1H here, and there should now be a signal that integrates to 1H. Do you know whereabouts that would show up?
Actually, no, because it's alcohol.
Yeah, so it's not on your correlation table where an alcohol's hydrogen shows up in NMR. But it's not as far left as you'd think. The only other OH that's on there is the OH of the carboxylic acid. And that is the farthest left signal that we see in the NMR. But the alcohol does a lot more hydrogen bonding, which means it gets a lot more shielded, which means that its signal usually shows up from 0.5 to 5, which is a lot lower of a frequency than most people expect. But that's a good way of phrasing it. There would be a new signal that integrates to 1H that wasn't there before. What other change? Interpret this however you might like. What other change would you expect to see between these two NMRs? Where do you see that?
Like 6.5 to 8.5.
And it should integrate to 5H. Because I didn't have any aromatic hydrogens before, and now I do have aromatic hydrogens. Any other changes that you guys would expect to see? Jordan's been getting very specific, which is great. You can take a broader view as well.
There would just be more hydrogens also.
More signals, for one. More integration, a higher integration. More total signals. A higher total integration. I will often phrase these types of questions as an increase in integration between. So I probably would have said increase in integration between 6.5 and 8.5. Yes, I would expect to see that because I should have had no integration between 6.5 and 8.5 before. Now I should have something to integrate. An increase in integration between 2 and 4 ppm. 2 and 4 is roughly when things are adjacent to a functional group, and this benzyl is adjacent to a functional group, and it wasn't there before, so that should be increased. But I've also lost my carbonyl position, so these CH2s, yeah, this one's a little bit more challenging to do for NMR. Think about what you'd expect to see and rationalize those changes. You need to be able to assign protons to what region you'd expect to see them in. Are they functional group adjacent? Are they more so just alkane? Are they in the aromatic ring region, the vanillic region, the aldehyde or carboxylic acid region? And you can lean on that correlation table, but if you don't know how to use that correlation table, it doesn't get you anywhere. All right. Good then? And you guys know there will be bonus points for spectroscopy as well. I almost always give a chemical reaction relevant to what we've been learning the last several weeks, or 2 or 3, and then spectra that correlate with the starting material and the products, if the products form. And then I give points for determining the structure from spectra and for annotating, for showing that you know how to pull information out of the IR. All right. Layla, I think this was your question, oxidation and degree of substitution. What I want to clarify about it is oxidation of what? Because we've done different types of oxidation. If you remember benzylic oxidation, we said that as long as an aromatic ring had a benzylic hydrogen, that it could be oxidized into a benzoic acid. I will admit I don't know where it limits, because I've actually given you guys some problems that I've thought about the reality of how it would function. So we said back in our benzylic chapter that if I treat this with a strong oxidizing agent, I essentially char any of the side chains so long as it has a benzylic hydrogen. So the methyl, the ethyl, the isopropyl all have a benzylic hydrogen, all get oxidized to benzoic acid, but the tert-butyl doesn't. I gave you guys this the other day. Oh, this was on your homework, right? Notice how I didn't oxidize the benzylic hydrogen or the benzylic carbon. There is a benzylic hydrogen in that structure, but I didn't create benzoic acid, which tells us that oxidizing the benzylic position is maybe not a last resort for the oxidizing agent, but going for the benzylic carbon is not as easy as going for the alcohol oxygen. It's easy enough to oxidize alcohols. My goodness, you've already got an oxygen there. You're one step closer. It's more energetically challenging to oxidize a benzylic position than it is to oxidize an alcohol position. Did that cross your mind at all? How come I'm able to oxidize just the alcohol here and not the benzylic position? It's okay. I didn't expect it to, but that's my job, is to try and make this make sense. I'm not sure if I can. So oxidizing alcohols, this is what your question really entailed, right? Because oxidizing the benzylic position, we didn't have a choice. We only use strong oxidizers. But oxidizing alcohols, we have selective oxidizers. If I introduce this compound to MnO2, this same alcohol, what happens? Your favorite letters?
NR.
No reaction occurs because manganese dioxide is only reactive if the radical intermediate can be stabilized by the aromatic ring or stabilized by resonance. So MnO2 only works at benzylic or allylic positions. And if I treat this with PCC, I don't get a carboxylic acid, I get an aldehyde. So one of them, Layla, is more oxidized than the other. I think it is kind of convenient sometimes that we called it being oxidized, because it's almost always because of oxygen. But it's not always because of oxygen. So which of these products is more oxidized? The benzoic acid from the primary alcohol or the aldehyde from the primary alcohol? Which one is more oxidized? Why did I say benzoic acid? I didn't mean that. The carboxylic acid. The carboxylic acid is more oxidized? Because it literally has more oxygens bonded to the carbon. It is more oxygenized. And in order for chromic acid to make a carboxylic acid, chromic acid has to first remove one of the hydrogens from that carbon. And chromic acid does that easily. What is not always obvious is that chromic acid does remove a hydrogen while also converting the OH. Chromic acid doesn't preserve this OH from the alcohol into the carboxylic acid. Chromic acid oxidizes the OH and then further oxidizes the aldehyde. So if I have a reagent that can oxidize the OH into an aldehyde, but cannot oxidize the aldehyde, we'll call that a mild oxidizing agent. It's only able to do one of the two possible oxidations. So that, Layla, is a primary alcohol. And things change when we look at secondary alcohols. Because a secondary alcohol only has one hydrogen to remove. It can actually be oxidized further, and we'll talk about that after the midterm. But with the reagents that we have, this is the end of the oxidation. It's got that one hydrogen to remove, and it removes it. And how do I oxidize a tertiary alcohol? You move to Texas. Because you see how oxidizing that tertiary alcohol means creating 5 bonds to carbon, which is famously cursed. Can't oxidize a tertiary alcohol because there's no hydrogen to remove to replace with a second bond to oxygen. So why do I say you have to move to Texas? Texas has the saying, everything's bigger in Texas. And so 5 bonded carbons are often referred to as Texas carbons. Bigger valency, bigger coordination number, more bonds, Texas carbon. Doesn't happen. So it actually wouldn't matter. If you introduced this with PCC, if you introduced this with chromic acid, you'd find no reaction occurs. Can I clarify or can I go in any further, Layla, with your question?
No, I think that was all that we needed.
Okay. You've got to identify, is it a primary or secondary carbon? I guess we didn't talk about methyl alcohols, but there's really only two possibilities for methanol. Oxidize methanol with chromic acid and make carbon dioxide and water. It will oxidize it fully. Oxidize methanol with PCC and you get formaldehyde, just a CH2O. All right. Any other follow-ups on oxidation? I was meeting with Johnny Pope, who's a tutor at the STEM Center in the SI building. He's there like every day. His hours are posted on our, we have a page, free STEM tutoring. You guys should go see him. He's really bored. He needs some OChem students to talk through. He's actually helped me proof the exams for tomorrow to make sure there's no errors. So if you pay him a lot of money, he might just try to remember what some of the questions were to give you the answers for them. And he was talking about epoxide ring opening. He said, on my drive over today, I was thinking about this. That's a dangerous sign, by the way, if you ever just find yourself daydreaming about epoxide ring openings. Be careful. Two things that epoxides can do. Epoxides can be opened in basic conditions as they are, or epoxides can become protonated and then opened. Now, epoxides are reactive, but it's not like they're explosively reactive. Epoxides are stable enough. And I know that can feel weird, but three-membered rings are not inherently cursed. Three-membered rings exist all the time in all sorts of stuff. So this three-membered ring needs a good nucleophile. Remember, in SN1 and SN2, we differentiated between something that is a strong nucleophile or like a strong magnet getting pulled towards an electrophile. Doesn't require a lot of work to do that nucleophilic attack. But a weak nucleophile, essentially a weak magnet, doesn't get pulled to an electrophile very well, doesn't really have the energy that it needs to react. So if I were to try and use water to open this epoxide, in non-acidic conditions, water is just not a strong enough nucleophile. The water here is unlikely to open the epoxide. But if I add hydroxide to it, now I have a strong nucleophile. And if I have two reagents present, one that is bad at doing its job and one that is good at doing its job, I can expect the job will get done because of the one that is good at doing its job. So hydroxide here will act as a nucleophile. If hydroxide acts as a nucleophile, which of the positions will it attack? Well, because we're in basic conditions, there's going to be this excess electron density, this excess negative charge. And those negative charges are better stabilized. I want you guys to answer this. Negative charges are better stabilized on which type of carbon? Can you put it into words?
Yeah, the less substituted.
Negative charge is more stable on less substituted carbons. When did I tell you that?
I think you told it while we were doing epoxy.
Probably. But,
Is that wrong?
but
I think
when,
you did tell me.
but when else could you have figured that out?
Oh, well, when we talked about carbocations.
I agree. Back in OChem 1, the first time that we talked about carbocations, you should have been able to predict the charge of carbon ions. What's the difference between a positive charge on a carbon and a negative charge on a carbon? Lack of electron density versus excess of electron density. They're opposites of each other. What's the difference? Everything is the difference. So if a positive charge is more stable when it's shrouded by electron density, more substituted, then a negative charge is more stable when it's free of electron density, less substituted. If they're opposites of each other, their trends should be opposite. The only trend that's not opposite, they're stabilized by resonance, because resonance is always a stabilizing force. So hydroxide here attacks at the least substituted carbon and breaks it open in that first step. And then it is useful to do an aqueous workup. And I say it's useful to do an aqueous workup because there is an acid-base equilibrium between water and the newly formed alkoxide. But guess what? It's like a 50-50 equilibrium. Not great. So if you want to make sure that 100% is turned into an alcohol, you need to provide acidic conditions. You need to protonate everything that's present. So an acid workup is useful here. If you run this in acidic conditions, then you cannot provide hydroxide. For instance, you can't write over the arrow H plus OH minus. It doesn't work that way. Why? It would just be water. You would just neutralize both reagents. So what you could say is H plus and H2O. Well, guess what? H2O is still a bad nucleophile. So it's not going to open the ring. But H plus will protonate the ring. And now that the ring has been protonated, it's more reactive. The ring is more likely to be opened once it's protonated. So water, being a weaker nucleophile, is able to open the ring when it's more reactive. I see. I think I added a carbon.
Do we number the reagents 1 and 2, or do we add them together?
We would add acid and water together. We would add an acidic aqueous solution. The idea of a 1-2 step is important. And applying 1-2 when it's not relevant is also important. So being able to say these need to be done separately is just as important as being able to say these need to be done together. H plus and water have to be added together. H plus and alcohol have to be added together. H plus and hydroxide have to be added separate. H plus and alkoxide have to be added separate. It's a good question. All right, so Layla, should we do a couple of problems then?
Yeah.
Applying it? Okay. Oh, I'm curious, how many of you guys were able to go through the roadmap worksheet from last class, last week? Yeah? Challenging? Yeah? Which side challenged you more, do you think? The side that was just reagents or the side that was, what am I trying to say? The side that was just reagents or the side that was just structures? Sorry, that wasn't clear enough actually. The one where you had to predict reagents or the one where you had to predict structures? Predicting structures was the most challenging. Okay. Yeah, to be fair, you were given no clues throughout any of it. You were given a starting material, and then everything, if you make one mistake, you get you're kind of screwed, right? All right, so let's say I have this alkene, and I want to get to this alcohol. Tell me what steps I need to do in between. And then say I have this alkene, and I want to get to this alcohol. Portable binder. Yes, but I wouldn't list them as separate steps.
Okay.
Right.
Yeah, that's why I was asking, because I was doing that. I was like, wait.
Let me demonstrate that on the board when we go through it to clarify what the distinction would be. Feel like you got it?
I think so. I'm not sure about that.
So here you have a 5-bonded carbon. Do you see how this carbon had 4 bonds?
Yeah.
Now it has 4 and a new one. This reagent, I mean, it's not common for us to balance an oxygen with magnesium. It's not wrong to, but we typically would balance it by like sodium, NaOCH3, or potassium, KOCH3. But you know what charge magnesium has? +2. because it's a group 2 metal. And you know what charge oxygen has in the context of an alkoxide? It's a -1. So they're just not balanced to each other. But this would be nucleophilic, and this is not really electrophilic. It's not looking to accept electrons at all. So what we want to do instead is something that will turn this into an epoxide. The reason I say we want an epoxide is because of the vicinal group that we get. You know that term vicinal? It's actually related to the word vicinity. And vicinity is like, we're all in each other's vicinity right now. Or like if you're in the vicinity of a crime scene, you're a suspect.
Okay.
These are in the vicinity of each other. They're vicinal, 1, 2. So a vicinal alcohol ether, that is what tells me an epoxide ring opening has just happened. And this too is a vicinal new carbon-carbon bond to alcohol. So I think this has to come from an epoxide ring opening as well.
Okay.
This works, this first step, but do you notice that you lost a carbon? There's the carbon in the ring, the carbon outside. There would be a carbon like that, yep. But although this works, it won't help us get to our final product. We need to make an epoxide instead. Do you know how to make your epoxides? Two ways. Let's use 2 different methods of making an epoxide here. What's one method?
MCPPA.
Yeah, metachloroperoxybenzoic acid, which is a type of peroxy acid. Keep in mind that is not a carboxylic acid because it's not CO2H. It's a peroxy acid, CO3H. And that's useful in making an epoxide. All right, now the context that we were looking at, the regiochemistry of epoxide ring openings, should have been a good indicator that you should get an epoxide in this synthesis. But there is another indicator that you should get an epoxide in this synthesis. If I map my carbons as just 1, 2, 1, 2, what I notice is that at carbon 1, I get a new group, and at carbon 2, I get an alcohol. This is that vicinal relationship. 2 new groups, one of them being an alcohol, vicinal to each other. That vicinal relationship is what tells me I should open an epoxide. Because with an epoxide opening, a new group adds at one position and kicks off the oxygen to stay at the other position. You start with a 2 carbon system, you end with a 2 carbon system that now has 2 different groups. Well, sometimes different groups, sometimes not different groups. Well, in this case, one of the groups I want to make is a new carbon-carbon bond. I want to form a bond from benzene to carbon 1. And we've not talked about a lot of different ways to make carbon-carbon bonds. And in the context of epoxides, there's really just one useful, no, that's not true. There's 2 useful ways. One of them is cyanide. I don't think cyanide is going to help me create an aromatic ring. Cyanide is not going to help me bring a phenyl group. But Grignards are very useful, and I can put a Grignard on just about anything. Now, acidic versus basic conditions. Is the Grignard basic conditions requiring an acid workup, or is the Grignard acidic conditions not requiring an acid workup, or does it only matter which side I want to attack? That's how I decide whether to do the Grignard in basic conditions or do the Grignard in acidic conditions. it can only be basic. Because like we said earlier, Grignards can't exist in the presence of acid. There is no way to do an acidic version of a Grignard epoxide ring opening. There's only the basic condition. So I will say first, I'm going to introduce phenyl Grignard because I notice I'm not adding that CH2, it's already present. I want to add the benzene directly. So the benzene will be the attacker, and follow that with an aqueous workup. What does the aqueous workup do? What's the point? It protonates the oxygen, so it turns an alkoxide into an alcohol. It also would destroy any unreacted Grignard, which is useful because if my Grignard is an excess reagent and it's still floating around, and then I take this and I try to go on to a new step, I might just be reacting my Grignard with other stuff later on, which is not ideal. Organic chemists sometimes refer to that as quenching. You guys know what else you quench? Quench a fire, yeah. Yeah, actually, I was just at a campsite up in Mill Creek Canyon on Friday, and the fire ranger came by and was like, make sure you douse that, quench it really good. She's actually an organic chemistry professor at Westminster, which was a funny overlap. Quench your thirst. So it's like to destroy, but usually because you've added water to it. And you know what you destroy if you add water to it? Grignards. They get quenched. They get destroyed in the presence of water. All right. How about my other one? What's my other way of making an epoxide? Good. This one has to be shown as two steps if we just want to show the epoxide. Because first we need a halohydrin. And we cannot do this without the halohydrin being formed first. Then we deprotonate the halohydrin. Chiral, achiral, or meso, this epoxide? Chiral, achiral, or meso? Raise your hand for chiral. Oh, 2.5, 3.5. Raise your hand for achiral. 1. Chiral carbon or achiral carbon?
That's the question.
It's got a methyl, a carbon in the ring that is part of the epoxide, a carbon in the ring that is not a part of the epoxide, and then the oxygen. So that's 4 distinct groups. Chiral carbon or achiral carbon? Chiral. It's got a hydrogen, the oxygen, the carbon in the ring that is not part of the epoxide, the carbon in the ring that is part of the epoxide. So 2 chiral carbons, which means that it's not achiral, but it's either chiral or meso. It's only meso if those 2 chiral carbons are symmetric to each other. Is there symmetry between the 2 chiral carbons? No, because one is a tertiary carbon and one is a secondary. They're not symmetric to each other. They're not the same. Chiral molecule. 2 chiral centers. Now, I know that I wanted an epoxide because I have 2 vicinal groups. carbons 1 and 2 now have an alcohol and an ether. That's a good evidence that I've opened an epoxide, especially since one of them is an alcohol. It's good evidence that I've opened an epoxide. But here the regiochemistry matters. When I've opened the epoxide with a Grignard, I could only attack the less substituted carbon because I could only do this reaction in basic conditions. Now that I'm doing this with to form an ether, I can do this in basic conditions with an alkoxide, RO-, or I can do it in acidic conditions with an alcohol, and that will change whether my nucleophile attacks less substituted or more substituted. So, which of these groups is my nucleophile? Did the alcohol form because of the nucleophilic attack? Sorry, did the oxygen of the alcohol come from the nucleophile, or did the oxygen of the ether come from the nucleophile? How do you know that?
You couldn't add the carbon group to the oxygen of the epoxy.
Right. There was no methyl here already. So where would that methyl come from if not from the nucleophile? So my nucleophile was the ether's oxygen, and that has attacked the more substituted carbon. So I need a positively charged epoxide. So here's what Justice showed for this. I hope that's okay that I call you out on that, Justice. Justice showed this as first H3O plus, then the alcohol. And is it obvious that the alcohol needs to be methyl alcohol to provide the methyl group? What's wrong with this is that the acid is necessary with the alcohol. I don't need to first get everything protonated and then add in the nucleophile. I want to provide both of them at the same time so that when the acid has protonated the epoxide, the nucleophile is already present to attack it. So this would have been better written just H3O plus with alcohol, or honestly, I would write it as H plus. We'll talk more in the second half of the semester about the difference between H plus and H3O plus. All H3O plus can be written as H plus, but not all H plus needs to be H3O plus. In terms of points loss, if you did not give me 1 and 2 with the Grignard step, you would lose 1 out of 2 points in a roadmap. Every box is 2 points. In a roadmap, you'd lose half of the points for not showing me first then second, because what you are communicating is dump these guys in together, which is, legal. It just won't give you what you need. So you're not quite there. You're not understanding half of the importance is the 1 and 2. Here, if you gave me 1 and 2, I would take maybe a quarter point off, maybe half a point off. Because the 1 and 2 doesn't impede the ability for it to work. It just wouldn't make any sense. You would probably have added all of that at once. But it's not impossible if you do it as a 1-2. So there are different times where 1-2 are very much necessary and times where 1-2 are better left off, but not necessarily impossible. You got 2.5 minutes. You got any lingering questions? Concerns about how the time will go tomorrow? I like to give reminders during my exams. So halfway through, I'll speak up and tell you that you're halfway through. 10 minutes remaining, I'll give a verbal reminder. And then with 2 minutes left, I usually encourage people to make sure that all of their questions have an answer and start bringing things to the front. Your cheat sheets are yours. So whatever you prepare, keep it, because it could be useful for your studying for the final as well. Okay? See you guys tomorrow.